Here's a general ordering of orbitals for multi-electron atoms. What we see is that the 1s is the lowest energy. Energy is increasing here on the y-axis. So we do start with the 1s. Then we see the 2s followed by the 2p. P's are a little bit higher in energy than s's. Then we see the 3s and the 3p. But here comes the idea of penetration. There is something called sublevel splitting. And with sublevel splitting, what we get is an uneven order of orbitals. The 4 is technically higher than 3, but the s orbital is technically lower than the d's. So what we'll see is that the 3d's are higher in energy than the 4s's. Then come the 4p's, and again, more sublevel splitting, the 5s, and then the 4d's. No, you do not have to memorize this order. What's really important, again, is being able to use the periodic table. But what I want to do before doing the periodic table is actually use this chart so we can start getting familiar with it to fill in some electron configurations. This is our map. This is the map that we are going to use to say, if I have an element like lithium, lithium has 3 electrons, where am I gonna put those electrons? Well, I always want to start at the bottom, the lowest energy possible. There's 1 electron there in the 1s. I know because of the Pauli exclusion principle, I can put a second electron in there as long as the spin is opposite. I can't put 3 in one orbital, only 2 in an orbital. So then I have to move up to the next one. The off-bow principle says I build up. Well, there are my 3 electrons. I could say that 1 was in n equals 1, L equals 0, ML equals 0, MS is plus 1/2. This guy could be that one. The next one is n equals 1, L equals 0, ML equals 0, and MS equals minus 1/2. That could be my other electron. Pauli exclusion principle satisfied. Those 2 electrons do not have the same 4 quantum numbers. For my last electron, n equals 2, L equals 0, ML equals 0, and MS can either equal plus 1/2 or minus 1/2. It doesn't matter. Choose one just so that you have it written down. And there's that guy. Yeah? That is how we would draw the orbital diagram and the quantum numbers for it. Now, electron configurations are our shorthand notation. We want to abbreviate. In the 1s orbital, there are 2 electrons. In the 2s orbital, there's 1 electron. That is the overall electron configuration. Notice that the overall exponents should add up to the electron count, and that is our final end of the day electron configuration. It tells us a huge amount of information about not only quantum numbers, orientations, spins, and energies of the electrons within this element. Let's try another one. I'm going to go ahead and erase these. I'll keep our data for lithium way up here so that we can move forward. Let's go ahead and look at carbon. Carbon is on the periodic table in row 2. It has 6 electrons. Let's go ahead and build up. 1, 2, 3, 4. There's the off-bow principle and the Pauli exclusion principle working for us. Now we get to degenerate orbitals. Don't forget Hund's rule. 5, 6. So off-bow tells us down here. And to move up, The Pauli exclusion principle says don't put more than 2 electrons on each line. And Hund's rule says, hey, don't pair those 2 electrons, put them in each orbital, 1 in each, because that's what we have room for. Again, X, Y, and Z there. Now, shorthand electron configuration here. 1s2, 2s2, 2p2. We do not see Hund's rule with the idea of the X and the Y and the Z, but we know it's there. It's understood for chemists. This is the full electron configuration then for carbon. Let's do another one. Let's get a little bit bigger. Let's go to sodium. Sodium on the periodic table has 11 electrons. Start at the bottom, work our way up. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Notice how I completed the 2p orbitals after I put 1 in each. Then I was able to pair before moving on to the 3s, the higher energy orbital. Full electron configuration, 1s2, 2s2, 2p6, and 3s1. Here's where we get into a really cool observation between, take the whole thing, between lithium and sodium. Notice these 2 electron configurations. Now, they are in the same group. They are family members. And what do we notice about their electron configurations? Their outermost orbital is an s orbital with 1 electron. There's going to be some interesting facts about reactivity. Let's just move these aside so we can do a couple more. Let's go ahead and do phosphorus. Phosphorus has 15 electrons. And so let's build up from the bottom, and then we'll get into some abnormalities. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. 1s2, 2s2, 2p6, 3s2, 3p3. Again, always double check to make sure that your exponents add up to the overall electron count. And make sure you're following the off-bell principle, the Pauli exclusion principle, and Hund's rule. Now, transition metals. Most of the transition metals follow this lovely category. What we'll see is that transition metals end in the 3D block. They hang out here. Most everybody follows the same exact idea. I want to present some of the irregular ones before we move on. Let's go ahead and look at copper. Copper has 29 electrons. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. Hop over here. This is the next one. 21. What? 21, 22, 23, 24, 25, 26, 27, 28, 29. Now, just like Hund's rule from before, D orbitals are degenerate, and so therefore 1 in each before we pair. So copper, we would predict, would have a 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and 3d10. Now here's the issue with sublevel splitting. It's the idea that yes, the 4s is lower in energy than the 3d, but this is not the actual electron configuration for copper. What happens in reality is this electron, I'll highlight that in a brighter color, one of the 4s electrons, one of the previous orbital electrons, can jump up into the 3d so that it can satisfy the complete 3d orbital. I should have said 3d9. Excuse me. So what happens is the 4s2 becomes a 4s1 and the 3d9 becomes a 3d10. So the actual electron configuration is 1s2, 2s2, 2p6, 3s2, 3p6, 4s1, 3d10. This only happens when a d orbital is d4 and it will go to d5, while the previous s goes from s2 to s1. Or the d orbital is a d9 and it will go to a d10, and the previous s will go from an s2 to an s1. It's when the d orbitals are almost half filled and they want to become half filled. There's a stability in half filling the d orbitals, and when the d orbitals are almost all full and it only takes one to become full. Only one electron can move. So copper and his family will see this experiment or this happen. Also, chromium. Chromium has 24 electrons. If we were to predict, we'd see the 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d4. And what we know happens when you see that 3d4, it's almost half filled. So scoop one electron from the previous s orbital, which would be the 4s, and pop it in that d. With the 5 and the 1. Reasoning for that is primarily because of the reactivity between and the energy difference between the 4s and the 3d. We can see it a little bit better here. They're very close in energy, these two orbitals. And so completing the n equals 3 is highly favorable versus completing just the 4s orbital. Excellent. Now, I said don't memorize the periodic table and don't memorize the order that we saw in this orbital diagram, the 1s, 2s, 2p, 3s, blah, blah, blah. You actually can read it on the periodic table. Here are the n values, 1, 2, 3, 4, 5. Here is the s block, the d block, and the p block. These guys down here, the F block. So let's say, for instance, we wanted to look back at phosphorus. You start, I'm going to highlight so that we don't block, but I'm going to highlight what would be helpful to look at. 1s, 2, 2s2, 2p6. Notice there's 1, 2, 3, 4, 5, 6 elements in that pink block and 6 electrons in the p orbitals. 3s2, 3p3. The third one over in the p block is that final electron for phosphorus. So we can look at any position on the periodic table and really be able to identify where that last electron went. So for instance, bromine, without even looking, I see he's in the P block, he's in row number 4, so I could predict that bromine has a final electron in the 4p orbital. He's 1, 2, 3, 4, the 5th element over. He should have his last orbital be a 4p5, and everything else is filled before it. That's the beauty of the periodic table. How it was set up did not have quantum mechanics in mind, but it fits perfectly. This quantum mechanical idea is amazing. So looking and reading from left to right, you can actually use the position of the element on the periodic table and understand what its final electrons look like. Now, a couple of definitions before we get into this category real quick. What I want to explain is that full electron configuration that we just did had some completeness to it. Specifically, if we look at things like argon. Argon on the periodic table has an electron configuration of 1s2, 2s2, 2p6, 3s2, 3p6. Its outer, all of its electrons are complete in this set. Why the noble gases are so inert, why they don't react, is because there's a completeness in their orbitals. They all end on a p6 filled orbital. And so what we actually can do for any other element, instead of writing the entire full electron configuration, we can write an inner or noble gas shorthand electron configuration. So something like selenium, we could write out the full 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, look at that, inner transition, or the transition metals there, 3p4. But that takes a really, really long time, and it takes a long amount of space. What we could do, instead of writing the full electron configuration, write what we call the shorthand. You take the previous noble gas, and then you write whatever is left over. Notice this is the exact same right here. Whatever's left over, we can write after that noble gas shorthand. Understanding that completeness is important. Now, the inner electron configuration not only helps us to write less, but it also gives us the idea of core electrons, stable electrons. The noble gases are so stable because of that completeness. And what that means is every other element's inner or core electrons are also just as stable. Anything we write after that shorthand, those can be reactive electrons. And so we'll dive into that as we get into periodic properties. Again, here's just the slide on understanding the transition metals. They're in row 4 to start off with scandium all the way to zinc. But again, the d orbitals are always going to be one less than the actual row number. So These are the 3 Ds, and these ones are the 4 Ds. So they're one less. That's one way of being able to avoid the memorization of those periodic elements, the transition metals. Notice again, just highlighted here, chromium and copper's group with its weird, not predictable electron configuration. That's something you do need to know. What I want to talk about a little bit more are the definition of core electrons. These are the innermost electrons. They are going to be stable, represented by a noble gas configuration. And we also have the valence electrons. These are the outermost electrons. These electrons are reactive. So we'll be able to look at those outermost electrons to understand physical and chemical properties. And they include the electrons in the s and p orbitals of the highest unfilled n value. So just to bring up another example, we can look at something like chlorine, which has a noble gas shorthand of neon 3s2 3p5. Overall, 7 electrons in chlorine's valence, 10 electrons in chlorine's core. Whatever is represented by that noble gas configuration, the Ne, neon, is atomic number 10, so 10 electrons for that neutral element. Those 10 electrons that chlorine also has with the same electron configuration are core, stable, non-reactive, innermost electrons. The outer electrons are what chlorine can actually play with and do reactions with. To compare, let's go ahead and just pull a normal transition element, manganese. Its previous noble gas is argon, 4s2 3d5. Notice this is the predicted. It's not, we do not change any of the s's and the d's. Because the d is half filled already, we're stable, we're good. Valence electrons, he's got 2. Notice we don't count the d's. Argon is 18, so manganese has 18 core electrons. These are d orbitals. They don't count. They're not part of the noble gas core, so they're not core. And they're not part of the valence because valence is only s and p's. That's it. Excellent. We'll get into elemental properties next time. We'll also get into the electron configurations of cations and anions. Thank you very much for joining me.